Hello everyone. My name is Megha and I'm a PhD student at Monash University. I'm working with Professor Alexander Higa and Professor Daniel Price. And today I will be talking about Timmy, who dared to drink the Holy Grail. So most galaxies have supermassive black holes at their centers, which are surrounded by stars. One such star is our friend Timmy, who got too close to the supermassive black hole and encountered a tidal disruption event. So, in a tidal disruption event, the self-gravitational forces of the star can be overcome by the gravitational forces of the black hole. And the distance at which this takes place is called the tidal radius, which is given by this formula here. There are two possible outcomes. One is a full tidal disruption event, where the star is completely ripped apart, as shown in this figure. And the other one is a partial tidal disruption event, where a remnant is left behind. So these disruption events were first detected by the Rosetta Stone survey in the 1990s. And we parameterize the strength of the encounter by something called the beta parameter, which is the ratio of the tidal distance to the barycenter distance. So whenever I talk about beta parameter in my slides later, whenever you see a bigger value of beta compared to a lower value, I want you to think that higher beta means stronger encounter with the black hole compared to a lower value. So it's been proposed that theorized that about 10,000 to 100,000 stars in the galactic center of our Milky Way galaxy have had an encounter with the supermassive black hole and survived. Hence, understanding the properties of such stars post-disruption is important. To do this, I used two different codes. I used a stellar evolution code called Kepler, which is maintained by my supervisor Alexander Higa, and a three-dimensional smooth particle hydrodynamics code called Phantom, which has been written by my supervisor Daniel. So the steps we followed were as follows. We first generated our stellar models from the stellar evolution code Kepler. Then we mapped these models into the three-dimensional smooth particle hydrodynamics code Phantom. And then we mapped these models back into the stellar evolution code to understand the post-disruption evolution of our remnants. So what kind of stars did we use in our simulations? We used 1, 3, and 10 solar mass stars at 3 different stages of their lives. We used the 0H main sequence, where the star has just started burning hydrogen in its core. The middle H main sequence, where the star has burnt about half of the hydrogen in its core, and terminal H main sequence, where it has burnt about 99% of the hydrogen in its core. This figure here shows the HR diagram along with all the models that were used for this paper. So in total, we used 9 different models. So then we mapped these models back into Phantom and disrupted our stars there. We used 1 million SPH particles for our stars. We considered general relativistic effects and a black hole with no spin and mass of 1 million solar masses. So I'll just show you some simulation results now. This one is a beta value of 0.85, which is a weak encounter of a 1 solar mass 0H main sequence star with a supermassive black hole. As you just saw, it's a very weak encounter. The star only loses about 10% of its mass, and then it can go and live its life. This second case is the same model, but disrupted at a much higher beta value of 1.49. As we can see here, the star is completely ripped apart, and as the simulation evolves, we will see that material falls back onto itself and then results in the formation of a remnant at about 33 hours. So what did we consider as a remnant from the streams and other material that was stripped away from the star? So to determine what is part of a remnant, we considered the condition that the potential energy plus kinetic energy and the internal energy should be less than 0. We also considered that kinetic energy should be less than half of the potential energy, which is based on the Virial theorem, and ensured that only particles close to the maximum density particle, which is the which we considered as the center of the star, were considered as part of the remnant. We also removed streams from our models. So in most of our simulations, we had these stream of material. For example, this 3 solar mass ZAMS model at 8 days. It has a remnant mass of about 2 solar masses, and we still had this stream of material. And to map these models back into Kepler, which is our stellar evolution code, we had to remove these streams. And to do that, I looked at the temperature profiles and found that the streams sort of clump together at a certain temperature, and then we removed these streams for all of our remnants. So how do these remnants look like? This figure here shows some of our simulations. So I particularly showed the middle age main sequence stars for 1, 3, and 10 solar masses for a range of beta values. So all of these these are basically the remnants after we had determined what is part of remnant based on the energy condition and also removing the streams. So we found that when the star gets close to the supermassive black hole, it undergoes compression, as shown in this figure for a 3 solar mass middle-aged main sequence star. We show the maximum density as function of time. So time is since the pericenter passage. So 0 means at the time of pericenter passage. And as we can see here, for higher beta values, which mean stronger encounters, there is more compression that takes place in the star, and then eventually the density decreases. We also found that there is oscillations in this remnant, and it's close to the fundamental mode. So this plot here now shows the mass of our remnants as function of this penetration factor, which is the strength of the encounter. We have plotted all of our models here. The key takeaway I want you to have from this plot is that more evolved stars can survive closer to the supermassive black hole, as shown for the orange lines. So orange lines show 1 solar mass stars. The dotted lines are the 0-age main sequence models, and the dotted dashed lines are the terminal age main sequence models. And as we can see here, the more evolved stars can survive the encounter closer to the black hole. And it's because as the star evolves, the density in the core increases. Moreover, the star's size increases as well, making it resistant to the gravitational forces of the black hole. We have also plotted the functional form given by Ryu et al. In their paper from 2020 for comparison with our middle age main sequence models. So our remnants formed for 1 and 10 solar mass stars lie within the range that they suggested. But for the 3 solar mass stars at middle age main sequence, we can see that our remnants are a bit more massive than what their functional form predicted. And there are 2 possible explanations. One is that we disrupted all of our models on hyperbolic orbits, while Ryu et al. Basically disrupted their models on parabolic orbits. Moreover, they use stellar MESA for their models, while we use Kepler, so there might be a little bit of difference there as well. So this plot here shows the density of our remnants as function of a radius. We have also shown the density of all of our particles here. And as we can see here, as the beta value increases, the density of the remnant decreases in the core, as I was discussing earlier. So when a star encounters the star due to that, but we found something different in our simulations. We found that there is formation of these vortices in our stars, which result in angular momentum transport, making the inner region rotate faster than the outer layer. So this figure here shows the 3 solar mass middle age main sequence star disrupted at a beta value of 1.79. The remnant has the mass of about 2 solar masses. Again, all times are with respect to the pericenter passage time. So as you can see here, there is this formation of vortices. I should mention that none of our models had any rotation profiles at the beginning of the simulations. So this figure here shows the rotation as function of radius. And the key takeaway of this plot is that the central region of the star rotates rigidly, while the outer layers exhibit differential rotation for our remnants. We have also plotted the breakup velocities as dashed lines for comparison on these plots. So we found that tiny undergoes composition mixing as well. So this figure here shows 1 solar mass, 3 solar mass, and 10 solar mass middle-aged main sequence stars for a range of beta values. Again, higher beta means stronger encounter. And as we can see here, for example, for the 10 solar mass middle-aged main sequence star disrupted at a beta value of 2.15, which is a very strong encounter, we can see that the nitrogen-14 composition mixing takes place. Material is brought outside from the core, and we see something similar for other disruption events as well. So the main goal of was to bring these models back into the stellar evolution code Kepler and to evolve these remnants in there. And this figure here shows the HR diagram of our 1 solar mass model that we had originally generated in our stellar evolution code Kepler in orange line. And then the blue line shows the model, this same 1 solar mass model, which was mapped into phantom but not disrupted. And then we brought this model back into the stellar evolution code to see if our mapping procedure is successful or not. And as you can see here, the luminosity versus temperature plot is pretty similar for both the scenarios, which means that our mapping procedure was successful. So using this, we mapped back all of our remnants into the stellar evolution code. So this figure here shows the luminosity as function of temperature for middle-aged main sequence stars. And I have plotted here 10, 3, and 1 solar mass stars for a range of beta values. I want you to only focus on these two important cases in this figure. So this purple line here shows a remnant of 2.85 solar masses formed by disrupting a 10 solar mass star at beta value of 1.95. And the blue lines here correspond to 3 solar mass stars. So as we can see here, the remnant formed from a 10 solar mass star is more luminous compared to the 3 solar mass star. We see something similar for a remnant of 0.64 solar masses formed from the 3 solar masses star compared with a star remnant formed from a 1 solar mass star. And an explanation for this is that higher nitrogen composition in these remnants mean that the CN cycle results in hydrogen burning faster, which results in higher luminosities. So we also found that Tini has found the elixir of life. So here we show the luminosity as function of time for middle-aged main sequence models for 1, 3, and 10 solar mass stars for a range of beta values. And as we can see here, the stars which get close to the supermassive black hole, meaning they lose more mass, end up living on the main sequence longer. So we also looked at the carbon and nitrogen compositions of our remnants at Kelvin Helmholtz time, as shown in this figure. We have plotted them as function of penetration factor, which is the beta. Again, higher beta means stronger encounter. And as we can see there, the stronger encounters result in nitrogen increase in these remnants while decrease in the carbon, which possibly could be used as a signature for detecting these kind of stars in the future. So how different is a disrupted star from a non-disrupted star? So here we have plotted the remnants formed by disrupting the stars in phantom as solid lines, and the dashed lines show the stars that have the same mass as our remnants, but never encountered the supermassive black hole. So basically, these are just stars generated in the stellar evolution code, which never had an encounter with the black hole, but have the same mass as our remnant. We showed zero H main sequence, middle H main sequence, and terminal H main sequence models for 3 solar mass stars. All of these are HR diagrams. And as you can see here, the middle age main sequence models evolve similarly to the remnants to the stars which never had an encounter with the black hole. But for the middle age main sequence and terminal age main sequence, we can see that our remnants are more luminous compared to the stars which never had an encounter with the black hole. So we also wanted to see how different are these remnants to stars which only had their outer layers removed, which is what I'm calling here the stripped stars shown in the dashed lines. And the solid lines show the evolution of our remnants. And this is all for 10 solar mass terminal age main sequence models. We show the evolution at after 400,000 years. I've also plotted the Kelvin-Helmholtz time for all of our models as stars. So what we found was that the remnants, the stars which only had stripping, would be more luminous compared to stars, compared to our remnants. And the explanation is that the fallback causes a hydrogen-rich surface layer, unlike just stripping of the outer layers. And we also retain the pre-disruption composition in this core of our remnants, as shown in this figure for helium-4 composition as function of the enclosed mass of terminal age main sequence stars for a range of beta values. So in conclusion, stars can lose a lot of mass and still survive. The core rotates faster than the outer layers, and there's inversion of rotation profile due to the formation of vortices. Timmy and his friends have found the elixir of life. They're more nitrogen rich in their outer layers, and they are also overluminous stars. Thank you.
All right, thanks. Let's see, questions.
Okay, thanks for the nice talk. So I assume that when you are establishing stellar evolution models, these models are under the equilibrium condition, right? Because they satisfy the equation of the stellar structure.
Yeah, so these are actually not in equilibrium initially. That's why we consider the evolution profiles here after the Kelvin-Helmholtz time scale. So they take some time to get back into the hydrostatic equilibrium in the stellar evolution code.
Okay. Another thing is that you say you remove the streams from the outcome of your hydro simulations. How do you actually do that? Is that just
So this figure here shows the temperature in Kelvin and the radius in centimeters for one of our stars which had streams. So we found that the streams look like this clumped in temperature, and that's what we removed from all of our models. So all particles below this temperature were just removed.
Oh, you just manually cut off all these particles?
No, I actually wrote some code that can automatically determine what temperature it wants to cut at.
I mean is that you just ignore the existence of them when matching your stellar profile into these particles. Yeah. Okay, thanks.
Yeah, yeah.
Hi, great talk. I had a question about how the stripped stars look. Do you know if they look similar or different from stars stripped by other mechanisms, say binary evolution and mass transfer?
Oh, sorry, I haven't looked into that yet, but that's a good question. I will have a look into that in the future. Thank you.
Okay.
Thanks for the nice talk. I was just going to ask about, I mean, because we see this also in other cases where you heat up the envelope, I mean, of the star in stellar mergers. Actually, I have a few cases where you can see stars that are actually dimming back as they go back to thermal equilibrium. So, and I think that's the same thing here. You're producing a hot layer of matter in this transient phase that then has to cool back to back to hydrostatic equilibrium or to thermal equilibrium. I guess I'm wondering, what are the prospects for actually identifying these in the galactic center, these sources? How do you think we would go about identifying past events? I mean, they're going to probably fade back to thermal equilibrium pretty quickly relative to the time between disruptions. But anyways, just your general thoughts on can we look in the galactic center and find these guys? That's my question.
So I would think maybe something like this plot might help, because all of these evolutionary tracks are shown after the Kelvin-Helmholtz time, and I compared them with stars that have the same mass as a remnant, but they never encountered a black hole. But we can see that these remnants formed by disruption events are overluminous compared to stars which never had a black encounter with the supermassive black hole. So maybe that could be a way to detect them. I'm not sure.
but even before the Kelvin time, I mean, these are going to be much more luminous, I think, for a period of time, even before they settle onto thermal equilibrium. So I'm wondering, what is that time it takes them? I mean, could it be as long as 10,000 years, in which case there could be one of these in the galactic center that did this recently?
Sorry, I am not sure how to answer that. I'm sorry. I can think about it and get back to you.
No worries. We can. I'm probably not being very clear. Thanks.
See, any other questions? All right, then let's thank Megha again.